Hi, my name is Jim Roach. And I'm presenting on behalf of the co-PIs on this grant, many of whom are in this room, on our study, high-throughput, high-resolution 3D measurement of ethologically relevant rodent behavior in a dynamic environment. So to start with, there have been a lot of advancements recently in neural recordings, allowing us to measure the activity of hundreds, if not thousands, of neurons simultaneously. However, the resolution of neural recordings doesn't match the resolution of our ability to quantify the brain's principal output, i.e. behavior. There are a lot of defined human behavioral paradigms used by the field, such as the rotorod, the elevated plus maze, and more visual tasks like the visual water tank. These paradigms are precisely constrained, reliable, and reproducible. However, they're limited to a small set of behavioral variables, and more importantly, they're not ethologically relevant. Until recently, more naturalistic behavioral paradigms, such as the open field, have been limited to a small set of behavioral variables, only allowing us to look at things like velocity, turning, or total distance traveled. Modern advancements in machine learning techniques have allowed for key point tracking on the limbs and forepaws, but they struggle to do this in the open field due to occlusions, limiting their ethological relevance. So we're still limited to a small set of behavioral variables in the open field. But the increase in variables that we're able to study has allowed for the advent of more modern embedding techniques looking at things like behavioral syllables. However, with 2D based techniques, there's a difficulty comparing data when embedding, because here on the bottom, we're looking at the embedding from one camera to another and seeing that the cluster occupancy is more dictated by the angle of view. And this can apply to multiple setups using different resolutions due to the nature of the camera frame. We believe that 3D-based techniques have the ability to overcome these limitations. However, there hasn't been widespread adoption of these techniques. We believe that's due to the accessibility. Part of that has to do with the space requirement, difficult hardware setup, having to match frames from multiple cameras simultaneously. There's a difference in imaging conditions because these behavioral environments or the background is really defined by the room in which the arena is in. Meaning you have to manually label between each of these arenas. This is a comparison of the tracking on a new versus of a data set trained on an old arena compared to a new arena. And we're seeing a high level of variability in tracking. So the network's performance is really governed by the data set on which it's trained, which brings up the ethical usage of AI and the openness of these training data sets, not to mention the differences in key point placement is relatively opine between labs. So then you also have to deal with the complexities of camera calibration requiring an expert in machine vision to implement. And then there's cumbersome pre-processing requiring matching frames between arenas, assigning the correct calibration, having to do with network hyperparameters. But we believe we can overcome these limitations by standardization. And standardization allows us to scale, not just looking at one experiment in one lab, but being able to compare data between multiple labs simultaneously. And then with that, we enter the realm of big data, which necessitates processing multiple videos simultaneously, not just one. And then we're going to need a centralized repository to handle this data. So to start with, we have aim one, building a scalable environment for reproducible behavioral recordings. Aim two, extending behavioral quantification to multiple organisms during cricket hunting. Aim three, quantify the effects of neurodegenerative diseases in the context of natural behavior. So for aim one, we built an arena using 4 mirrors to bend light, allowing us to get 5 views from one camera, preventing while avoiding fisheye distortion and limiting the spatial footprint to 30 by 30 inches, allowing this to fit through a standard door frame, allowing for on-site delivery rather than having to assemble it in the room. Through this is what the camera sees, 4 side views and 1 bottom-up view, allowing for reliable reconstruction of the animal. And this is an example of 3D-based dance predictions. So on the left is the distribution of mean pixel reprojection error across 360
1 minute.
days. So we have a very robust tracking. And then we're able to use the same network on multiple arenas. In gray here, this network was never had a single frame contributed to the training data set. Aim two, extend tracking across multiple animals. This is a very rich, robust behavioral paradigm, allowing for more ethologically relevant dynamic recordings. Aim three, quantify the effects of neurodegenerative disorders such as Parkinson's and retinal degradation. So this is an example of tracking between a healthy animal and a Parkinsonian animal. So we're able to quantify the behavioral differences between these two paradigms. More importantly, we're able to do this in a distributed way, not just limited to one lab. We can just wheel in a new arena and have it work in a different, in the context of separate labs and contributors, allowing us to create a behavioral data set that grows and evolves, where we can characterize the differences of different treatments and how they're able to restore movement, not just looking at an increase in movement, which could be attributed to something like jitter, but seeing it in the context of restoring natural movement. Questions?